I'm Brian Huber. I'm chairman of the Department of Paleobiology and also curator of Foraminifera. Foraminifera are these things shown here. These are living forms, a benthic on the left, planktic on the left. Benthics live in the sediments, planktics float. Benthics have a record back to the Cambrian over 500 million years ago. Planktics have a fossil record back to about 200 million years ago. These both are extremely important for climate change, studies of evolution, and so forth because they're ubiquitous in the world ocean and found worldwide, and extremely valuable for interpreting paleodepth, paleotemperatures, and so forth. So I want to talk about my thread of research since my graduate school days, starting in Antarctica, where we worked in, of course, a polar environment, very harsh, no vegetation, yet we would stumble across swimming reptiles, cold-blooded reptile bones of a plesiosaur here, fossil wood in Antarctica. We had forests in Antarctica during the Cretaceous, about 70 million years ago. So what a contrast to be there and then see this and then really wonder why was climate so different and why did it change. It also is the place in Antarctica, this place called Seymour Island, where we discovered an extinction event of Foraminifera. And these are sample bags I collected through a section. We found abrupt extinction here, but we also found ammonites that went up to this level and they abruptly went extinct as well. So following that research, I did a lot of work with deep sea drilling program, the JOIDES resolution, and we cored a number of sites where in fact we got some beautiful Cretaceous tertiary boundary cores. This is one core from near Antarctica in the Indian Ocean, where again we see this very abrupt extinction. But this core in particular is extremely important because we got the entire impact event recorded in this bed right here. Foraminifera below, planktic Foraminifera go extinct. These are the new species and surviving species afterwards with all the telltales of the impact event itself. So we've published on this at several sites, and it's incredible to take apart these cores and be able to tell such detailed stories. Well, a lot of my work is also using the chemistry of the shells, and by analyzing that chemistry and making certain assumptions, we can then reconstruct temperature of climate through time. But this depends on having very well-preserved material like this shell here, which is 90 million years old, but the shell is perfectly preserved, unlike these other two shells here. On the left are examples of foraminifera from Tanzania, a program that we've been working on for the last 5 years. A 90 million year old foraminifera, planktic and benthic, perfectly preserved, again giving very reliable temperature estimates. Well, we've been focusing on these really well-preserved sites. This is a map for 90 million years ago. I'll mention something about this site here, 58 degrees south paleolatitude. In the cores, we see this really abrupt warming event, and the sediments just change very subtly in color. But we can see at 58 degrees south, temperatures of the surface water get up to 32 degrees centigrade. Meanwhile, the benthics are warm, but not nearly warm, of course, as the planktics, at about 12 degrees centigrade. This is one of those things where you don't expect it and you wonder what in the world happened. So this is an area that we're pursuing now. But when you look at this on a climate modeling output, in order to get these kind of temperatures at that latitude, we would have to have 7,500 ppm carbon dioxide to best explain those temperatures using the modern assumptions of how the ocean climate system worked. Well, obviously, something is wrong about our assumptions because you can't imagine an Earth with 7,500 ppm carbon dioxide. So a big disconnect between the climate models and the actual data. Well, this is a temperature curve from benthic foraminifera from about 1,000 meters water depth. This is a curve of a colleague through the Cenozoic. This is present day. This is the big ice sheet event as Antarctica glaciated. Going back in time, look at the Cretaceous temperatures, particularly this time interval called the Turonian. Deep sea temperatures, 1,000 meters depth of 16 degrees centigrade. And right here, we have this super greenhouse peak temperatures of 20 degrees centigrade at 1,000 meters depth. Today, those temperatures are about 2 degrees centigrade. So this is extreme warmth that we never imagined we would find. Well, to pursue this further, we've been working in Tanzania. We got funded by a collaborative grant through NSF, 3 years of drilling. This shows the intervals that we've cored from the Cretaceous time, and we focused on this Turonian time of extreme warmth, the so-called greenhouse, super greenhouse. So here we are in Tanzania, the southeast coastal Tanzania. These are marine sediments that have been gently uplifted on land, and those sediments are clay-rich, and they yield exquisitely preserved foraminifera. Well, not to go into details, other than these records are beautiful. These are fantastic records of benthic foraminifera on the left. These are the isotope values, and these are the temperatures that we get. And these are the planktics. All different species, very consistent results, no evidence of ice sheets during this time. And look at the temperatures we're getting at a site about 30 degrees south latitude, 32 degrees centigrade of the surface ocean. So again, this is an extremely warm Earth, verified by these beautifully preserved foraminifera. So with that, I'll stop and just mention that this is an international collaborative effort, and it's an ongoing effort. As you go back in time, the areas to explore these questions get smaller and smaller, but we continue in our quest to search for the best preserved Cretaceous age foraminifera to fill in the pieces of this climatic puzzle. Thank you.
What do you think caused this remarkable situation of heating in the Earth?
The question was, why did this extreme warmth occur during the Cretaceous? And it's not known specifically, but we do know that seafloor spreading rates, the rate at which ocean continents move on the Earth, was much faster during this time period. And the suggestion was that the gas from volcanoes under the ocean and worldwide produced a lot of CO2. So this was a high CO2 Earth. CO2, of course, is a greenhouse gas, and this gas then was the main forcing factor for the warming. But particular events are very puzzling because we cannot find linked volcanic explosions to explain these warming events. And another factor for the warmth of this time is the configuration of the continents. With the faster seafloor spreading, the volume of ocean in the ocean basins was basically pushed up so that more of the continents were flooded. And so actually, Kansas, Nebraska, they were covered by ocean all the way up through British Columbia. And so that ocean then holds heat much better than the reflective land. And as a result of that, oceans covering Antarctica, oceans covering much of the continent, just that by itself is going to give you a warmer Earth. But particular events and this extreme warmth is still puzzling. It's something the data modelers first didn't believe, but now we have enough evidence worldwide that yes, we know these temperatures are real, and now we have to figure out just what happened.
So what's your opinion?
I am very puzzled by this. The site that I showed in southern South Atlantic, we tried everything we could to explain those isotopic temperatures. We took apart those sediments. We did use different kinds of elemental analyses, and we cannot explain that abrupt warming itself. It's too warm for methane to have been frozen in the sea floor, so you can't have a methane release to explain this warmth. And so as a result, we are puzzled. You know, we have just a few sites to explain the climate of the Earth. And in order to get a better explanation, we've got to get more data, got to get more sites.